Okay, well, just got my second question, another magenta one. Makes sense. You guys would be asking about the hard ones. You're not going to ask about the easy ones. So this is from chapter 9, number 40. And the problem is asking to find the center of mass of a quarter of a circle object that has length L. And since it's a quarter of a circle, this would come down here and make a 90 degrees. And so where is the center of mass is the question on this. And maybe I'll just color this in. And hopefully one of the things you got out of the chapter was that the center of mass vector, center of mass, is equal to 1 over, and there's a nice little derivation that says the center of mass is this weighted average. That is, if you chopped it into a bunch of little pieces from I equaling, say, 1 to n, and then these are the little pieces, and this is the position, then depending on how much it weighs, that's why I call it a weighted average, because here you're adding them up and dividing by the total, but it's the weight of each one. So the center of mass is what we would call a weighted average. Of course, in a calculus form, we would say take this limit as the mass of the individual pieces go to 0. And so we would have something that looks like this. And this, again, is... how do I want to say? Just be careful with your symbolism here. You learned this in calculus that if you had a summation that you had a bunch of pieces so that they got smaller, so you had an infinite number of pieces you had adding up, this would become an integral. The tricky thing, though, I think, in this is paying close attention to what gets small, what goes to 0. And in this case, it's the mass of the object that goes to 0. And that might look a little foreign to you, because I know in your calculus class, you always had the limit as x goes to 0, and that's the variable x. But keep in mind that in your calculus class, you were not using the symbol x to represent position. You were using the symbol x to represent a variable. Something went small. Something got smaller and smaller and smaller. And so we're not saying the position goes to 0. That would be saying everything would go to the origin, and that's not at all what we mean here. We're not saying the position gets small. We're not trying to make all these positions go to 0. What we're trying to do is make each little chunk that we would add up get smaller. So looking at these two variables, the thing that goes to 0 is the mass. So that's why you have this calculus form. And again, they show that in the book too. So maybe all that was unnecessary. In fact, maybe even the next step is unnecessary. If we break that into its two integrals, we could find what is the center of mass in the x position by taking the x position and adding up all the mass. And we could also find the center of mass in the y position by doing the same logic. And again, this first one, maybe a little thought ought to be put into this, but I don't think we need to do a whole calculation. That's going to come out to be 0. And hopefully you can see that back in the picture here. If this is the mass, and you draw here a vertical line for the y-axis, then every little chunk over here is exactly matched over here. So that means you have some little chunk of mass. There is a negative x and a positive x at the same time. So the two of those together give you 0, and so you're adding up an infinite number of zeros when you group them together. And so again, this little chunk over here and this little chunk over here, when you added them together, would give you a 0. And so hopefully conceptually from the physics of it, you would and the math, you would say 0. And I guess the physics part of it is because I got equal sides, so the center of mass is going to be somewhere along this y-axis. And then the math of it is, I guess, more of a statement of, if you're going to add something up, we would say if you have an odd function added up over an even interval, you're going to get 0, because the even interval means you got just as many negatives as positive x's, and then the function is exactly equal and opposite on both sides. So anyways, that, again, maybe that's a long way of saying is 0. And so maybe I should have just began this whole description with the part that is challenging, and that is solving this integral. And that's really the hard part of this problem. Where is the center of mass along the y-axis? Because again, the x-axis is clearly 0, and the y-axis is clearly not 0. And then, of course, we've got to have some calculus. Anyway, so I thought that would be a nice little review in all of this. But finally, we can get to the meat of the problem right here. And so I'll continue. Capital M is the mass of the total thing, and then y is the position. And so again, if I come back over here to my picture, and maybe I look at this little chunk right there, its vertical position, I'll just kind of draw over, would be right here. And maybe the first thing going through my mind here is that if I say that this material, which is a quarter of a circle, has a radius of r, as we already said, it had length L, but it has r, then the y here is r cosine theta, where theta is this little angle here. And so you can see then we would be talking about starting maybe over here, where the angle is initially at maybe negative pi over 4. And then I would add up and 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 add up. And so doing my calculus, I would then add up to a positive pi over 4. And so there are my limits of my integration here. And of course, then what changes is the theta and not the r. And so there's that little triangle. And so this whole thing right here is the y. Now, I still have this dm, which probably is a little bothersome to you because, again, going back to this statement of what goes to 0, we're used to having the x go to 0. And that's, of course, I'll say it again, that's not what you mean in your calculus class. You meant x stood for some variable, not necessarily position. But, of course, on the other hand, you're going to be tempted to make the x go to 0 because you do know that position is involved here, and our limit's got to be our position. But it doesn't have to necessarily be the x position, and that's kind of what I'm showing here, where my limits are the theta, not the x. And so it would be nice then to switch this right here, this dm, into something involving the theta. And that's where the idea of density is going to come into play. Density can be thought of as the whole mass over the whole length, but it could also be thought of as a little bit of mass over a little bit of length. Now, notice I used the ds, and that's kind of the traditional symbol for an arc length. And so a little arc length I'll just call a ds. And so what I could do then is use this right here in here, and then call this then a rho ds. And so now I've gotten rid of the dm and something more related to space. Now it's not related to the angle yet, so I've got another step to do. But that right there is the dm from up here. All right, well, let's see what I have so far here. So it looks like I've got the M, total mass, still on the outside. But here was a big reason for that step is the R is a constant as you add up all of these pieces. And so constants can be pulled in front of the integral. So I'll pull the R out. And then also the density of it is a constant. And so here's the density. Notice, by the way, I this was the length density, the mass per length, as opposed to a volume density, since this is just really kind of a one-dimensional, it's a little curve, so we'd have to look at the mass per length. I still have my integral, and then the same limits. Okay. And then I have this cosine theta. And then this is where this s is going to come into play. The ancient Greeks defined an angle. And so let me come up here and point out that they said it's the arc length over the radius. And that's, how you get an angle in radians. And so I'm going to take advantage of that by writing this as r theta is equal to s. And so that means a small arc length is equal to r d theta. And I will use that then down here. And so that ds here becomes r d theta. And so another r can pull out. And so I'll take that r and move it here. So there's the r squared. And now I actually have a very easy integral to do. And so like most of our physics problems, you'll see the math really isn't the hard thing. It's getting to this point. And so it's really probably from here to here that is the hardest part of this problem here is getting to this, what I'll call an easy integral, not to belittle it, and there's still some more work to do. But an integral now of cosine theta is just sine theta. It's setting the limit from minus pi over 4 to plus pi over 4. Then gives me an r squared rho over m. And then I can put in my sine of pi over 4 minus the sine of a negative pi over 4. And as opposed to getting my calculator here, maybe I'll just remind myself that this right here is root 2 over 2. That's a terrible looking picture there. Root 2 over 2. And then this would be a negative root over 2. So there'd be two of them, and that would cancel off. So this is just root 2 right there. Of course, continuing on, I've got this r squared, I've got this m, and let me take advantage of this rho. And again, remember, we said earlier on that you can think of rho as either the whole mass over the whole length or a little bit of mass over the same little bit of length. And so let me do it this way now. So I can replace my rho with the whole m over the whole L. And so there's my density, and then I have the root 2. And so the m's cancel off. And so I have r squared root 2. And it depends what direction you want to go at this point, but let's talk about the L. The L is a quarter of a circle. And we know that the circumference of a circle is 2 pi r. And so this could be written then as pi over 2r. And so this becomes pi over 2r. And then one of the r's cancel off, and I get a 2 root 2 r in the numerator, and a pi downstairs. Now, if I grab my calculator here, let's see what I get. 2 times the square root of 2, then divided by pi is 90%. So 90% of r is the result. Although perhaps I'm not quite done, because the problem did say, where is it from the top down? And see, I put my grid down here at the center of the arc, so it's 90% up. So maybe we'll go to another page here. But if I kind of redraw this picture, then the center of mass would be down 10% of R. And so it's at the center and down 10%. And I guess technically it's done, but I did look at the solutions, and they wrote it in terms of L. So why don't I go one more step and come back here and remind you that earlier we said L was pi over 2R. And so that means we could put a 2L over pi in place of an R. And so we can write how much it's below in terms of the length of the arc. And so grabbing the calculator again, 0.1 times 2 divided by pi is about 0.06, why don't I just call it a 4L below. And so whether you want to say it's 10% R below or 6.4% of L down below at the center of it, there's our answer. All right.